Okay, welcome to one more videos on memories. In the last video, we were discussing the usage of floating gate avalanche MOSFET if it is in the ROM configuration. So, major advantages of this FAMOS MOSFET in the ROM array is that we can able to reuse the same structure for storing any values of in any bit, that is you can either score 0 or 1. The major disadvantage with this type of FAMOS is that we cannot reuse it for very large number of reconfiguration, because we will going to end up with the damage of the floating gate structure, because for every erase of the data that is changing the threshold voltage, we are supposed to go through that exposure of the devices through to the ultraviolet rays, which will going to damage the structure because the oxide layers are very thin in nature. And one more major thing in terms of disadvantage is that we know that we will be having this VDD which is being sometimes used as 5 volt and sometimes used as 20 volt, and this word line, so which will be usually 2.5 volt, you can see now 2.5 volt, or it can be something like sometimes 20 volt also, which will be the gate voltage. So because if you want to modify the threshold voltage, the same word line should be made equal to 20 volt while increasing the threshold voltage. While reading the value, it should be 2.5. The same with the case of this VDD, so it should be 20 volt or 5 volt depending on whether you are storing the value or you are reading the value. So that poses a lot of challenges in the life of in the aging of the devices. So these two are the major disadvantages with FAMOS. So looking at the major problem of not the reusability of these type of MOSFETs for large number of reconfiguration. So next type of again the non-volatile memories are Flotox. So this Flotox is nothing but a floating gate tunneling oxide. So the structure of this Flotox MOSFET, so this is Flotox MOSFET which comes out from floating gate. This is tunneling oxide MOSFET. So here this is also a floating type of MOSFET. Only thing is that the structure that is used for this will be slightly different, and the main advantage of this particular type of Flotox MOSFET is that the values, the threshold voltages can be increased or brought back to the earlier value using the electrical voltages. No need to expose the devices to ultraviolet rays, so that we can able to increase the lifetime of the devices. The cross-sectional view of this Flotox just looks like this. Suppose if you are considering this as the MOSFET structure in terms of this is P substrate, and if you have this as N plus, and if you are considering this as drain and gate, of course this is usually how the FAMOS looks like. But only thing is that we're going to have a gate structure which is floating slightly different compared to that of FAMOS. This is how the structure looks like. Now this is the gate structure. Now this is a major difference that comes over here. You can see here, this is drain, this is gate, the floating gate structure. Usually these dimensions are in terms of 20 to 30 nanometers of separation, whereas this particular thing will be hardly 10 nanometer in terms of dimension. That is, towards the drain side, the gate will be bit more closer to the drain side as compared to the source here. So at source you're going to have maybe around 20 to 30 nanometer separation, whereas over here it will be hardly 10 nanometer separation. So because of this particular physical structure of the floating gate towards the gate side, so it so happens that even if you apply VGD is equal to around 10 volt, which results in a potential electric field of, this is 10 volt per okay, maybe a nanometer. So 10 volt per nanometer will comes out to be electric field of 10 into 10 power 9 volt per meter. So this will be 10 power 9 volt per meter of electric field will be applied between the gate and the drain. That will have lot of tunneling of charges to the gate and to the drain depending on the polarity of the gate to drain voltage. Mean to say, the IV characteristics of this particular MOSFET with respect to only drain and the gate. Suppose if you are calling this as VGD, suppose if VGD applied is very large, so it happens so that I can able to make it to turn on at a larger voltage. Suppose if you are applying larger, so under normal conditions, suppose if you are not applying too much of voltage to the gate and drain is usually, of course, assume that this is 0 volt and this is 5 volt, and if you are having 2.5 volt, so under normal operation the threshold voltage is around 0.5. This 2.5 voltage will make the transistor to turn on. Assume that I want to increase the threshold voltage of this. So in order to increase the threshold voltage of this, as in the previous case, we are supposed to have some charges to be trapped in this. So to have the charges to be trapped in this type of gate structure, what they will do is they will apply something like, okay, 20 volt is applied here and here it is grounded. Since you have a very large potential across drain the gate, the charges will be stored in this because there is a possibility of tunneling. So because of this 20 volt and 0 volt, or maybe hardly 10 volt, we're going to have too much of electric field will be generated. That will going to certainly make the electrons to be get accumulated here. When electrons get accumulated, we're going to have the larger value of the threshold voltage. Similarly, if you reverse the polarity of this VGD, suppose if VGD is negative, I can able to make the threshold voltage lesser. So now in this particular Flotox type of MOSFET, it is possible to have both the charges of negative or positive charge can be stored here. If you are applying VGD of positive voltage, the threshold voltage is now positive. If you apply the VGD which is negative in voltage, then you can able to certainly reduce the threshold voltage of this MOSFET. Since it is electrically itself possible to change the threshold voltage, either the increment or decrement, so this comes under the category of electrically erasable program read-only memory. Now here this was just okay, EEPROM. So this was actually EEPROM because you can electrically program the ROM. So this was EEPROM because you can electrically program. If you want to erase anything, so you may have to put the entire structure in UV light. Whereas when it comes to the devices using Flotox, so it is now electrically erasable program read-only memory. So you can certainly program it. So how do you program? If you want to store a 1, so don't change the threshold voltage. If you want to store a 0, change the threshold voltage. How do I change the threshold voltage? Make sure that you have VGD sufficiently high enough so that for normal gate voltages they should not turn on. So once it is not turning on, so then it is considered as 0 being stored. So how do I suppose if I want to reuse the same thing, then how do I get it back to the previous value? You apply the reverse voltage between gate and the drain so that it goes back to the original value of the threshold voltage. So since it is electrically possible to bring the threshold voltage back to its original value, so that's what is said as electrically erasable program read-only memory. Of course, the symbol of this particular type of MOSFET looks like something like this. So this is also a floating gate, but this is an extra configuration indicating that this is a Flotox, that is towards the drain side you have much more closer gate structure than at the source side. So this Flotox MOSFET are used in these type of memory arrays. So one more disadvantage with this MOSFET, this floating gate MOSFET in EEPROM is that, because as we discussed, the gate voltage will be sometimes made 20 volt and gate voltage will be made 2.5 volt during the storage time or during the programming time and during the access time. What I mean by access time is, suppose if you want to read whether the value stored is 0 or 1, you'll be applying 2.5 volt. That 2.5 volt that you're applying is to access the value of these transistor, whether it is storing 0 or 1. The programming time is, or the programming voltage is, suppose if you want to store a 0 onto this, you have to increase the threshold voltage. So during that point this should be made 20. So as we discussed there in the previous case, so this word line should have different voltages depending on whether you are programming or accessing the device. Whereas when it comes to Flotox, so it can have a slightly different configuration. So assume that this is your bit line, and this is your word line. Instead of having a single MOSFET for both storing as well as programming, what can be done is, of course, assume that this is VDD. So what can be done is, so assume that this is your bit line, this is your word line, this is bit line. So we can have something like this. So this is the normal access transistor. Now let us consider this transistor, which is whose threshold voltage can be modified. Let me just ground it. So this is now VDD. Now this is that Flotox. This is the normal MOSFET. So if I say this is M1, this is M2. M1 is normal NMOS structure, and M2 is actually Flotox MOSFET. It's a Flotox MOSFET. Now let us see how does this is going to work. Assume that I want to store a 1 here. Assume that if you want to store a 1 here, so you are assuming that the threshold voltage of this earlier it was 0.5. Since it is 0.5 earlier threshold voltage, you make this VDD equal to 5 volt and make this word line as 2.5. Of course, so what you can do is, now when this is 2.5, when this is equal to 5 volt, you can see, suppose assume that you are connecting this to VDD. So assume that you are connecting this to VDD. So whenever it is connected to VDD, so what you'll get here is since VDD is equal to 5 volt and word line is equal to 2.5, you can see this will have the current will flow here. The bit line will be, what will be the bit line for this particular configuration? Since this is equal to 5 volt, so whenever the threshold voltage of this is also 0.5, this is also, of course, this will always have a threshold voltage of 0.5, whereas this is going to have a threshold voltage of either 0.5 or it can be maybe around 10 volt. When this is 5 volt and 10 volt, when the threshold voltage is either 0.5 or 10 volt, so the operation of this device purely depend on what is the threshold voltage. So for the time being, let us assume that the threshold voltage of this is not modified and it is equal to 0.5. When the threshold voltage of this is 0.5, if you apply this as 2.5 volt, this is on, this is also on, so that the current will flow here, and you're going to get a 0. Meaning, if at all, if you want to store a 0, don't change the value. Don't increase the threshold voltage. Now assume that if you want to store a 1 here, so what should happen? You increase the threshold voltage of this. So how do I increase the threshold voltage of this? The threshold voltage of this is increased in such a way that you make this VGD greater than 10 volt, then this threshold voltage increases. Okay, assume that it just increases to maybe around 6 volt or 7 volt. Whenever you apply 5 volt, this is off. When you apply 2.5 volts, this is on. Even though this is on, since this is off, there is no drop here. Whatever voltage you have will be get stored here. Meaning, if at all, if you want to store a bit 1 here, you have to make this with an increased threshold voltage. If you want to store a value of 0 here, you keep the threshold voltage of this like 0.5. So how do I keep the threshold voltage of this to a larger value? So during the programming period, you will be changing only this transistor. You will not be changing the configuration of this transistor. Meaning, you'll be simply turning on this transistor, whereas applying large voltage or small voltage during the programming time, you'll be you'll be using this particular Flotox transistor, whereas this ordinary transistor will be used during the access operation. So assume that you didn't change the threshold voltage of this. If you don't change the threshold voltage of this, whenever you apply 5 volt to this VDD and this word line is 2.5, the current flows and entire thing will drop here. You'll end up with a 0 voltage. Assume that you want to store a 1 here. You want to store a 1 in this bit. In such case, increase the threshold voltage, apply 2.5. This will be on, whereas this will be off, because for 5 volt this will not turn on because its threshold voltage is increased. So there is no drop here. You're going to get the bit line as equal to 1. So this is the of course one of the major advantages that supposing that you have increased the threshold voltage of this to 10 volt. If you want to bring it back to the lesser voltage, what you can do is you can apply the VGD equal to negative 10 volt, then whatever charge that was stored there will be get restored. It will going to have a reduced threshold voltage. So since we can able to program it either to a lesser threshold voltage or a larger threshold voltage using the electrical voltage between the gate and source, it is called as electrically erasable programmable read-only memory. So this way we can able to improvise the circuit. One more important thing is that word line need not have to change very often. So this value of VDD will be changed whenever you want to change the storage value of this one. Whenever you want to change or modify the threshold voltage. Otherwise, this voltage will also be usually 5 volts. So in the next video, we'll see how to use the flash memories for reading and writing the parameters.